Good morning. We're going to go ahead and get started. Once again, I'm Mary Hall from University of Utah, and I am introducing the FCRC 2019 speakers. These speakers were selected by the conferences for their the interdisciplinary impact of their work. And this week's talks have shared a common theme about new applications, unprecedented scalability, and societal impact. And today we're gonna have a talk that really focuses on the societal impact of things, how data science can be used to address societal challenges. Our speaker is Jeannette from Columbia University, and she's had a career that spans academic, industry, and governmental organizations. She is at Columbia University now, also had a long career at Carnegie Mellon, served as vice president at Microsoft Research, and as assistant director for NSF's SIZE Directorate. She received the CRA Distinguished Service Award in 2011, the ACM Distinguished Service Award in 2014, and she's a fellow of AAAS, ACM, and IEEE. With that, I'd like to introduce Jeannette.
Thank you, Mary. Thank you, everyone, and I'd like to thank the organizers for inviting me to give this presentation, and thank you for coming. I wanted to talk about data science, and specifically data science at Columbia University. And the tagline that I use, data for good, and what I mean by that. Let me start with the bigger picture, what I like to call the data lifecycle, to put into context what data science is all about. It, of course, starts with generating data. We generate lots and lots of data, but lots and lots of data have also been generated, if we remember, by large scientific instruments, so the Large Hadron Collider, large telescopes, neutrino detectors in the South Pole. For decades already, the scientists have been generating lots and lots of data. I think one of the new things in the recent history is why we're so excited about big data and data science is that it's the amount of data that we, people, are generating that others are collecting about us. I have a whole other talk about the fairness of that, but I'm going to save that for later. So in any case, we generate lots and lots of data, and then this data is collected. Not all data generated is collected. We do some processing, and by processing, I'm throwing in everything from encryption to compression, but also data cleaning, data wrangling, all the kind of stuff that might happen before you actually store the data, lay it down in some storage medium. We, of course, will store the data in some way through data management techniques, database techniques, such that we can retrieve this data very efficiently later. And then, of course, there's analysis. Now, I think it's analysis, and by that I'm throwing in deep learning, machine learning, AI, data mining, all the analysis techniques that we have had and cultivated in the past few years. That is what is making data science so exciting to not just we in the computer science community, but outside. Every single sector, every single profession is getting very excited about, can I use deep learning for my data set? So it's usually data analysis that gets the attention of people outside of computing with respect to what data science is. But I wanted to put this in context with respect to the whole data life cycle, because each of these phases is very important. After analysis, of course, we have to visualize the data. It's not enough to spit out some probabilities or some numbers. We actually have to visualize the data so that we can interpret the data in some way so that the end user can do something with that analysis. It was not until I joined Columbia University when I actually added the last phase in my life cycle chart I call interpretation. It's when I was talking to my colleagues in the journalism school, and they said, Jeannette, it's not enough to just visualize the data. It's not enough to just show pie charts and bar graphs and so on. You have to tell a story about what it is the end user is supposed to get out of that visualization, to get out of that analysis. So the journalists like to call that storytelling. I just use a more neutral term, data interpretation. But in the end, it is an end user. For now, we still have human beings at the other end who are taking the results of the interpretation and doing something with them, making a decision, doing a prediction, and so on. So throughout this entire data life cycle, I very much emphasize the importance of the privacy and ethical concerns of collecting the data, analyzing the data, telling stories about the data, and so on. So this is very much underlying my advocacy for data for good. So what is data science? I have a very succinct definition that I'd like to share with you. Data science is the study of extracting value from data. There are two important words in this definition. The most important word is the word value. Value is deliberately subject to the interpretation of the end user. So to a scientist, value is discovering new knowledge. To a business person, the CEO of a company, value is actually calculable. It's bottom line, it's number of clicks, however, a company might actually accrue value because of the data, for instance, that it collects about us. To a policymaker, the value of data comes into helping the policymaker make decisions. So for instance, a mayor in a coastal city should be paying attention to data that says something about sea level rise. So all of that is a different kind of value for the end user. The other important word in this definition is extracting. The point is, it takes a lot of work to get this value from this data. So I want to share with you my three-part mission statement for the Data Science Institute at Columbia University. The first is advance state-of-the-art in data science. This is really speaking about basic research, pushing the frontiers of data science, as it itself is a new emerging field. So we in academia are still trying to figure out what this data science field looks like. Meanwhile, we are continue to make advances in the underpinnings, the foundations of data science. At Columbia, we define the foundations of data science to stand on three pillars of strength: computer science, statistics, and operations research. But we also have a lot of colleagues in signal processing from EE participating in defining the foundations of data science. The second part of my mission statement really speaks to the breadth of the university, and that is to transform all fields, professions, and sectors through the application of data science. I thought when I first joined Columbia 2 years ago that I would have to go around talking with all the deans and the department chairs and faculty. I thought I would have to cajole them into the importance of data science, the analytical techniques that we are using for analyzing data. It's been just the opposite. They've been knocking at my door saying, we really need data science expertise. We know this data and data science techniques are going to transform my own discipline. And I'm getting this down the line, whether they're in the medical school or the history department or architecture. And those are quite enjoyable conversations, and it's quite a surprise to me. So the transformation is actually just happening under my nose. The last part of my mission statement really speaks to the data for good tagline. And this is ensure the responsible use of data to benefit society. To benefit society speaks to the societal grand challenges that we scientists and engineers and also humanists really aim to tackle in terms of helping humanity, helping society. I'm talking about healthcare, climate change, energy, social justice, and so on. It's the ensure the responsible use part of that mission statement that I'm really passionate about, because this really speaks to the privacy and ethical concerns about data science, and so on. So, as I mentioned, my tagline is Data for Good. This really stands for two things. One is using data for good to benefit society, but also using data in a good manner, in a responsible manner. At Columbia, we have over 350 affiliated faculty with the Data Science Institute coming from all 16 schools, colleges, and institutes throughout the university. And they literally are coming from all walks of life, all different disciplines, all different professions. We loosely structured the Data Science Institute around some thematic centers. These are just one way for me to have a reach into the entire university. Some of these themes are quite obvious, like smart cities being in New York City, but also we have one in health analytics, one in business and financial analytics, and so on. We have a very strong master's in data science program. I'll just run through this quickly, just to say that the demand continues to grow. Our program is rigorous, and everyone gets a job after they graduate. We just started a PhD specialization in data science. This is mainly for students who are already enrolled in certain PhD programs in the engineering school and in statistics. They can take additional courses and get a PhD specialization. We also have something going on with Columbia Entrepreneurship. We call it the Collaboratory, where faculty from 2 or more different disciplines come together, design and co-teach a course to bring data science, computer science, and technology to these other disciplines. Probably one of the most successful is actually not one course, but a curriculum that's offered by the business school. It's a sequence of 8 courses, and now 50% of the MBAs coming out of Columbia Business School have had some exposure to data science. We have a robust industry affiliates program. Some of the sponsors of FCRC their logos are up there as well. And we have international representation. You'll see some well-known Chinese companies. There's a Brazilian company, and so on. So at any one point in time, we have about 25 different companies that are affiliated with this program. One of the benefits the affiliate gets is to help with the capstone course that's part of our master's program. They have access to a team of master's students who work on a real-world data set answering real-world questions. And then just last year, we created a partnership with IBM on a Center for Blockchain and Data Transparency. And this is something that is organized along research, education, and entrepreneurship. Okay, so now what I wanted to do, what I really wanted to do is share some research stories with you. And this really will start, I'll key off my mission statement, sharing only one story having to do with advancing state-of-the-art. It has to do with causal inference. And then I'll share little snippets of other stories to show how expansive data science is at Columbia University, and on a few stories having to do with the societal challenges and also privacy, ethical concerns, and so on. So let me start with multiple causal inference. Causal inference, of course, has been a long-standing interest, not just in computer science, but of course statistics, but in other fields, in the social sciences and economics. Causality is, being able to conclude causality is really the bread and butter of some of these fields. This work is done by Yixing Wang and David Bly, and it's addressing a slightly different problem. It's addressing the problem of not single causal inference, but multiple causal inference, recognizing that that's actually the more common situation. If you want to understand some effect on, say, a medication, in fact, there are multiple causes that may lead to that particular effect. And it turns out that solving the multiple causal inference problem is slightly easier than solving the long-standing problem of single or univariate causal inference. So let me set up an example to give you a concrete way to think about the problem that they are addressing. Let's pretend I am a producer of movies, and I want to produce a new movie, and I want to decide which actors to place in my movie. So the actors I choose are the causes, and the revenue that I get from the movie is what I'd like to estimate. At my disposal is a database that has, for a movie, here are the actors, and here's how much money that particular movie made. And you can see immediately, so what I want to do mathematically, and this is the potential outcomes rendition of what I need to compute, is really the estimated potential outcomes of if I place this set of actors in my movie, how much money will I make? In the Pearl approach to causal inference, one would write it something like that. This is just for those of you in the audience who are familiar with causal inference. So in classical causal, so the problem, of course, with causal inference is that there are multiple confounders, and these confounders can affect both the causes and the effect. So, if, say, the genre of a movie is a kind of confounder where it's going to determine what actors I put in my movie, because I'm certainly, there's certain actors who play well in, action movies versus artsy movies, and also the genre could affect the effect in that action movies tend to make more than artsy movies. Also, whether a movie is a sequel is going to be a confounder, because likely to choose actors who were in the first version of the movie for my sequel, et cetera, et cetera. So this is actually, this multiple causal situation is actually quite common in genetics. So what genes affect a trait, and choosing actors for a movie is like choosing athletes for a sports team, choosing the prices that you're going to put on items in a supermarket will help determine how much people spend, et cetera, et cetera. So in classical causal inference, the way in which we estimate causal effect is first you think of all the confounders, sequel, genre. Sometimes you put one actor in a movie because they kind of go well together with other actors. All these are potential confounders. So in classical causal inference, your first job is to think of all the confounders. And then you, measuring all those confounders, you then can estimate the causal effect by, and the W sub i's are the confounders there. You add those confounders on for each of the movies, and then you can iterate. So there's an iterative process that allows you to estimate causal effects. That's what the little equation on the right basically stands for. So I already said confounders can affect both the causes and the outcomes, and we need to correct for all the confounders. That's what's going on the right-hand side, which requires, in theory, in principle, that we have identified and measured all the confounders. But that is actually a very strong assumption. It's untestable, and it's called strong ignorability. The assumption is that there are no unobserved confounders. So we have to think and think and think and think, make sure we thought of all the confounders, and then we can play this little algorithm out. And so that's the way it is. So the new idea is this idea called the deconfounder. And let me just operationalize it for you. The first thing you do is you, there we go. The first thing you do is you fit a local latent variable model of the assigned causes. Those are the possible assigned causes, the observables, using something like factor analysis. And then you can actually test whether this model is good or not against some objective function that you define. And then you use those as substitute confounders, and then play the same iterative process in doing the estimate of the causal effects. So the main point is this. If I can find a factor model that captures the population distribution of all the assigned possible causes, then I will have discovered a variable that captures all multiple cause confounders. So the multiple cause confounders are really inducing a dependence on the variables of the assigned possible causes. And so now you don't get anything for free here. There is still an assumption. And that assumption is that there's no observed single cause confounder. But it's a weaker assumption than for the single causal inference problem. So it's a weaker assumption. The model that you build is, you can check it for certain properties. So there's an operational or computational element there. And then the authors prove in the paper itself that the deconfounder gives you unbiased causal inference. So this is an example of basically pushing the state of the art in causal inference, in this particular case, in data science more generally. Let me come back to movies, just to put this in concrete terms. So this is a snippet of a 007 James Bond movie. That's Sean Connery in the middle. He plays 007, James Bond. And then there are these two other actors, each of whom play the characters Q and M. With the deconfounder, Sean Connery's value goes up, and the characters who play Q and M, their values go down. Another way to say that is, without the deconfounder, the value of Sean Connery is underestimated, and the values of the characters who play Q and M are overestimated. And intuitively, that should make sense to you, because for the longest time, when Sean Connery was 007, you went to see the next James Bond movie because he was 007. And so with this model, of course, you can play a lot of what-if questions, answer a lot of what-if questions. So just to summarize this story, the deconfounder corrects for unobserved confounders like genre, sequel, and so on. Okay, so now what I want to do, switching gears, is to just run through a series of examples of how data science is used in other disciplines. Let me start with something pretty obvious, and this is, again, recognizing that the science community has been working in big data for decades. And the example I want to start with is biology. And we all know at the turn of the century, with the Human Genome Project, we knew that big data was going to really revolutionize biology. And now with DNA sequencers pumping out data like mad, there's a lot we can do with all this data. In this particular example, the researchers were studying the microbiome of pancreatic tumor cells. And just with DNA sequencing of the microbiome and the cancer cells, they discovered that the microbiome was counteracting the effect of the chemotherapy that was meant to treat the cancer. So that's not good. But they went one step further, and they saw that if you inject an antibiotic into the tumor cells, then the antibiotic would counteract the effect of the microbiome, thereby making the chemotherapy effective. And that was really all through analyzing big data. So that's my biology story. There are many, many such stories out there. My next story is about astronomy, and I believe Daniel Shu, the co-author on this paper, is in the audience. So you can ask him about the details of this work. I think the astronomy community in general is very forward-thinking. They have so much data that they're very open to using techniques that come out of computer science or statistics or anywhere if these techniques can help them manage all this data. So in this particular case, the astronomers and the data scientists were working together to look at weak gravitational lens data. This is data that the astronomy community is trying to understand. and build models for and estimate cosmological parameters for in this, what's called the lambda cold dark matter model. And what they found is that, yes, with the CNNs, they were able to better estimate those cosmological parameters above and beyond traditional statistical techniques. Now, this was all done on simulated data. More recently, I know that they've been wanting to use real data to do the same analysis. But this gave them a glimmer of hope that, yet again, deep learning has yet another astonishing success in yet another discipline. Somehow that moved beyond me. Let me turn to a completely different discipline. This is economics. In economics, people are always interested in understanding cause and effect. This particular work is using this technique that came out of the economics community called double machine learning. And they were looking at the question of whether online markets, online labor markets like Amazon Mechanical Turk behave like regular markets. And what they discovered is that, in fact, they behave more like monopsonies than any kind of free market. And one example of, a monopoly is when you have one seller, multiple buyers. A monopsony is when you have one buyer, multiple sellers. So it turns out that Amazon Mechanical Turk and the like behave more like monopsonies. And one example data point that they use to justify this conclusion is to show that high reward tasks, for instance, do not get chosen, picked up more by, say, Turkers than low reward tasks. You'd imagine that if you want to make a lot of money, you go after the high reward tasks. But instead, you can go after a lot of little reward tasks and make your money. Another example is in finance. So the finance industry have been already putting out these things called robo-advisors. If you happen to be wealthy, you might have a personal financial advisor, but right now the industry is looking at these robo-advisors to give you personal advice. Now, when you have a human being as your personal financial advisor, it takes some amount of time, usually months, perhaps years, for that financial advisor to learn your investment preferences. Are you conservative and you want to keep all your money under the mattress? Or are you very courageous and you try all sorts of crazy instruments out there? Or somewhere in between. So what this robo-advising work is trying to do is to actually predict the investor preferences using, in particular, this one equation here that you're all familiar with probably is using reinforcement learning. And just automating this allowed this particular team of researchers to, just in basically 8 or 9 iterations of the algorithm, learn investor preferences. So this is all simulation data. This particular group of researchers actually want to work with some real financial institution that has real data to test out the idea. For something completely different, we have a very modern history department at Columbia. Many of the faculty are using data science, topic modeling, NLP, sentiment analysis routinely in their work. And this is one example I wanted to share with you. There's a history faculty member at Columbia who amasses every year all the declassified documents that come out of the federal government. So every year there's a release of documents that's published, and this particular person just is accumulating all of them. And one set of documents that he analyzed just to see if he could determine anomalous events was some cablegrams that diplomats sent each other in the 1970s. So what he wanted to do was go through the contents of the cablegrams, the to field, the from field, and also the contents, the subject field, and so on, and see if he could detect the unusual events and identify whether those unusual events actually mapped to real historical events. And sure enough, every black dot there represents one of those unusual events. And some of them you'll recognize, like the evacuation of Saigon and the death of Mao Zedong. So, there. Okay, so that's our history department. So I now want to turn to the data for good, and I'll start with responsible use of data. And I know that there's a lot of talk in the computing community and beyond on FATE, I added the S for security and safety, fairness, accountability, transparency, ethics, the ACM now sponsors FAT Star and so on. I throw all of those into what I mean by responsible use. As I mentioned, my sole contribution to this acronym is S for safety and security. This is partly reflecting my own background. So I wanted to actually share two stories, research stories, and research efforts along those lines. So last year, my colleagues who were actually programming language, software engineering, formal methods type of people, borrowed, or let's say were inspired by two programming language and software engineering techniques and applied them to better understanding DNNs. And what they discovered, so one of those techniques is code coverage. So when you have a program, you usually want to test it by tickling all the paths in your program, covering all the code. So analogous to that, they define a notion of neuron coverage, where you'd like to tickle all the nodes in the network, all the edges, and so on. So that's very intuitively easy idea to understand. The other idea that they are borrowing from software engineering is the notion of differential testing. When you have two pieces of code that are supposed to compute the same answer, you see if they differ in some way. So if you have two DNNs that are supposed to do the same classification on, say, a set of images, you see where they differ. And so using those two ideas, they built a tool called Deep Explore that shows that at the time, all the state-of-the-art vision DNNs had flaws. So for instance, what they actually do is they take certain images and they systematically perturb them in natural ways such that the classifier will label it incorrectly. So in this particular case you see here, you have a typical image. This is the image system, the vision system in, say, your self-driving car. The self-driving car sees the guardrail in the image on the left, and the classifier says, veer to the left so that you don't go into the guardrail. That's fine. What their system does is automatically and systematically for all images perturb these images in a natural way. So in the natural way here is to darken the image, which is a very natural occurrence because we don't always drive in the sunlight. So by darkening the image, the classifier actually says veer to the right, and then you die. So that's the fatal error of these DNNs. They also applied this to other things besides images, malware detection, and so on. Another example I wanted to give has to do with privacy, but it's inspired by differential privacy, but it's more about robustness of, again, perturbing input images for DNNs. We all know how easy it is to fool a DNN by putting graffiti on a stop sign, and all of a sudden the DNN doesn't classify it as a stop sign, and again, you go through the intersection and you die, so that's not good. So instead of the testing approach where you sort of for each DNN, for each image you do something, wouldn't it be nicer if you could guarantee for some set of perturbations that you do to a set of images that you have some robustness guarantee at the end? So that's what this work, Pixel DP, is all about. And the idea is inspired by the stability guarantee that you get from differential privacy. So I know you had a whole talk by Cynthia on differential privacy. I'm not going to belabor that, but really the beauty behind differential privacy is not just that it's applicable to privacy, it's that it's actually a stability guarantee. And so what the solution that these researchers did was add a layer of noise to a DNN that will, at the end, guarantee some confidence interval around the prediction for each of the labels. And so this work is to appear in this year's or appeared in this year's Security and Privacy Conference. Okay, so now I want to turn to some of the societal grand challenges that we at Columbia like to work on. One I want to share with you is some work on social justice. This is some work that is done in collaboration between some natural language processing faculty and some faculty in the School of Social Work. They have looked at they're trying to understand how to reduce or intervene for gang violence. They looked at Chicago gang, and in particular, the tweets that the gang members sent each other. And the idea is, if you can do sentiment analysis on the tweets, then you may be able to intervene before any violent action happens. So the idea was then to look at their tweets and see if they can classify a tweet as being aggressive in sentiment or more about showing sadness as opposed to aggression. And so what happened first is, of course, before they could even get to that kind of classification, they had to analyze the language. It is its own language, so our NLP people had to do a parts of speech analysis because the language they use is heavy with emoticons, symbols, and words that we may not understand if we're not in that Chicago gang. And so that's the first thing they did. That parts of speech analysis is available online, so you can check it out yourself. And they were able to do that sentiment analysis, as I said, with the idea that if you can detect that the gang members are tweeting something that sounds aggressive, then a social worker or law enforcement can intervene before a physical act of violence occurs. So that's the story. We also have at Columbia one of the world's largest a group of climate scientists. This is at Lamont Doherty Earth Observatory, part of the Earth Institute. They amass many volumes of data, climate data from around the world, doing simulations at different levels of resolution for different parts of the Earth, oceans, and air, and so on. So what I'm showing you here is not so much the obvious, which is, oh, let's throw deep learning or machine learning at some of the data that they are analyzing. The climate scientists are doing that as I speak, but I also wanted to emphasize the systems nature of doing science. So Pangeo is actually an open source platform for all climate modelers, climate scientists to come together, to share data, to share algorithms, to share models, to share results. And you can see that it's funded by multiple organizations. And it's already being used for doing simulations on ocean turbulence, hydrology, meteorology, and so on. My last example of societal benefit is in healthcare. So this is a project called Odyssey. It's observational health data sciences and informatics. We pronounce it Odyssey. It's coordinated by Columbia University. It involves 25 different countries around the world. There are 80 or more different data sets that are federated, much like this conference is federated. But what's unique about this is that there are 600 million patient records in this federated data set. And now here's the amazing part. They're all in the same format. So when you have 600 million EHRs in the same format, you can actually do some very interesting analysis that you could not do through clinical trials and so on. So this group is really emphasizing the importance of observational data. When you have it at scale, then you can discover drug interactions, the effect of certain medications for treating certain kinds of diseases by just looking at the data. So one example I wanted to give, and this is quite a busy, but I have time, quite a busy visualization. And the reason I like showing this is to emphasize the importance of an earlier point I made. And that is, it's not enough to just show pretty pictures. Someone has to tell you a story about them. So in this Odyssey data set, each ring of circles represents one of those data clinics. So for instance, the ring of circles in the middle on top, you can't read it, is the Columbia University Medical Center. And I'm just showing you 9 different clinics and for 3 different diseases that they studied. So on the left is diabetes, in the middle is hypertension, and on the right is depression. Now let me tell you how to interpret each of those rings of circles. So what they are studying is what drugs are given to each patient to treat a particular disease. So for instance, if you're being treated for hypertension, that's the middle, and you're a patient at Columbia University Medical Center, that's the top rings of circles, the inner ring, and each patient is one radius through that ring of circles. So if I'm being treated at Columbia University Medical Center for hypertension, the first drug I'm given is represented by the color, there's a color coding here, the first medication in the inner ring of circles. And if all is fine, then I don't get treated with any other drug. But if that doesn't work, then I'm treated with a second drug. And that's represented by the second ring, a second circle around that, in that ring. And if that doesn't work, then I'm given a third drug, and so on and so forth. So each circle in a ring of circles represents a drug that I'm given in my sequence of medications treating me for that particular disease. I hope that makes sense. So now that I've interpreted each ring of circles for you, let me just give you a couple of observations that the researchers discovered in looking at the data, no clinical trials. First, for hypertension, if one were to collapse all the rings of circles into one big ring of circles, they found that 1/4 of the people treated for hypertension in this federated data set are treated uniquely. 1/4. So that means if you have hypertension and you're in that 1/4, and I'm your doctor and you say, Jeannette, is there anyone else in the world being treated like me? The answer would be no. That's amazing, astounding. It's one of those pieces of information that come at you after you look at the data. Now, to understand why is a whole other set of research questions to be answered. Another interesting observation made by looking at just the data is the lower left-hand corner so if you look at the left column, that is for treating diabetes. All of the other rings of circles pretty much look like the top two. There's this drug that's represented by the chartreuse ring that for the most part works. But you'll notice that in the lower left-hand corner, that chartreuse is very small in the first ring of circles. It turns out that lower left-hand corner stands for a Japanese medical clinic, data from a Japanese medical clinic. And in looking at the data, they surmised and discovered that the Japanese have a disposition against that particular drug represented by that chartreuse color. That is not shared by Chinese or Korean. It was really unique to, looking at the data, the Japanese in that medical center. So those are the kinds of things that one can glean when you have so much data. So what I wanted to do is close. I started by talking about multiple confounders. And what I wanted to do was to tie my first story back with this story. And this is really hot off the press results. I've never talked about this before. The work has just been put on archive 2 months ago. It's basically bringing these two together. So let's build a medical deconfounder. This is really preliminary work to go to show what could be done. And so what this group of researchers did was take the Odyssey data set and build these medical deconfounders for specific tasks, and then see what medications have a positive or negative effect on an indicator for a particular disease. And then they compared the results of their deconfounder model with medical literature. That was their validation mechanism. And what I wanted to share with you is just one example of what they were able to do with this medical deconfounder. And it's related to treatment effects on hemoglobin A1C, which is a protein that's an indicator for blood glucose levels, which is an indicator for diabetes. So the unadjusted model, and it was basically a linear regression model, is the equation on the expression on top. And then the deconfounder is the medical deconfounder is the expression in the middle. And I wanted to just give you the bottom lines. First of all, this deconfounder actually reduces both false positive and false negative. So for example, and now I'm not going to be able to pronounce these things properly, but acetaminophen in the unadjusted model indicated a causal effect. But in the deconfounder model, it goes from causal to non-causal. So acetaminophen is what's in Tylenol. And so maybe that's not a surprise. I mean, all of these are now, this is what they observe, and now they have to understand the why. In the middle, you'll see aspirin is there, which has, in both models, no causal effect. So maybe that's analogous to why Tylenol or acetaminophen should not. But I don't know. I'm not the medical scientist. On the other side, there are two drugs in amlodipine and hydrochlorothiazide that go the other way. In the unadjusted model, they showed to have no causal effect, but in the deconfounder model, they show to have a causal effect. And again, the medical scientists in the room can better explain what questions these results are asking, and then suggest further study. The other point I really wanted to make with this particular example is that this medical deconfounder is actually more consistent with the medical literature with respect to medications affecting increase or decrease of hemoglobin A1C. So this all gives us hope that this deconfounder idea actually can be very useful. It also gives us a different way to understand the massive amounts of medical information that we have, medical data that we're collecting. So I'm going to stop there. And data for good, just remember that's what data science at Columbia stands for. Thank you very much.
Vivek Sarkar, Georgia Tech. Is the mic on? Now it's working? Okay. Is this, yeah. So Jeannette, thanks for a wonderful talk. I was just wondering, for us as a CS research community, when you think of your mission, the three parts, advancing data science, impacting other fields, and promoting responsible use of data, where do you think we need to make the most headway, given where we are right now?
In computer science?
Yes. And computer science broadly.
I would say, to be perfectly honest, and now I'm speaking very pragmatically, given what's happening in the real world, I would say for computer science, and this is happening, I'm seeing this in many computer science departments, I would actually say the responsible use, data ethics, computer science ethics. I know, look, I never took an ethics course in my life. I was trained as a computer scientist, straight and narrow, and I love computer science. But now I'm seeing the implications of not understanding the consequences of the technology that we develop. And many of you are perhaps uncomfortable with nuanced questions, like ethical questions are always nuanced, and there's no right and wrong. But I think we need to face these, because if we don't, as technologists, then it will be the policymakers, it will be, not in consultation with us, it will be the policymakers making regulation or passing laws that that won't make sense. And I saw some of this when I was at the National Science Foundation, when there was a lot of interest in cybersecurity and a growing interest in privacy. And I remember seeing draft legislation on my desk saying, we should do this. And I'm saying, that doesn't make sense. And so, first of all, it does speak to the importance of scientists engaging with policymakers, something I think many of you know I've been promoting. But now, something that I've really come to appreciate being at Columbia University and talking to law professors and business school professors and journalists and people who are not techie by training, they grapple with really hard problems all the time, societal problems, where there is no right or wrong. There are nuances, there are debates, there are many sides to it. And it's uncomfortable for us, it's uncomfortable for me, because as a computer scientist especially, you like, black or white, yes or no, true or false, 0 or 1. But that's not the way the world is. So that would be something that we can, as a computer science community, work on together. It's one of the reasons that I'm promoting it for data science, because data science is new enough that we can get the ethics in from day one.
Thank you.
Thank you for the question.
Hi, Simon from Ohio State. Interesting talk. So what are your views on topological data analysis? You didn't mention this subject in your talk.
To be honest, I don't know a lot about topological data analysis.
Okay.
So I guess I don't have a view. I would say that if it's coming from the theoretical community or the topology community for mathematics, I have a colleague who works on that at Columbia. If it can help us understand big data from a structural point of view, where you can identify certain invariants about the data or invariants over the algorithms that manipulate that data, then I would say it's great stuff.
Okay, thank you.
Unfortunately, I'm not well-versed in that area.
Yes, hello, Ted Lair with the City of Austin. The question has three parts. The basic question is what's happening at Columbia. The motivation is that cities are responsible for collecting a lot of data. With smart cities, we're going to be collecting a lot more data. We have a responsibility to be open and transparent with that data. We have in Austin, we have programs to protect privacy. We don't think we have our act together, but we think we're making great progress. We're exploring differential privacy, for example. But we have a question about system impacts of data.
About what?
System. Let's call it community impacts of
Yeah.
data. I'll give you two examples which will focus the question for you. Recently, the Department of Housing, the Federal Department of Housing, sued Facebook, and I'm not calling Facebook a bad actor here. But they sued Facebook on the grounds that they allowed advertising to discriminate for housing and apartments, to discriminate against minorities, religious groups, that kind of thing. Because as you know how Facebook works, you can decide who you like to target your advertising at. And apparently they're being accused of targeting, excluding groups that might have been minority and that kind of thing. That's using data. There's a right involved there. That's not a privacy right. It's not a right of privacy here. We might claim there's a right to something else there.
It's a fairness issue.
It's a fairness issue, but it's a community right as well. The second piece is that we've experienced this in Austin, and maybe you're familiar with filter bubbles, how we're not even sure sometimes when we're talking to our community that we're being informed by the same information. We've had our own version of Pizzagate in Austin where it was unbelievable having the discussion with the community where we didn't have the same facts, so to speak. So my question, back to the original piece, is what is Columbia doing about addressing these kinds of problems? They're not privacies for you and me. They're system-level issues about what people do to the data and impact the system, meaning the community, as well as what are you doing to help improve the communities talking to each other so they have shared information or at least the same. I'm willing to have a conversation about fake news if that helps.
Yeah, so let me take those two questions separately. First of all, I happen to be on the New York City task force for accountable decision systems. This is, believe it or not, New York City passed legislation last year that basically is asking city agencies if they use these accountable decision systems and how can we be assured that they're using them in a non-discriminatory, in a fair way. This is an example of legislation, and then they want explanations and they want everything. This is an example where legislation is ahead of where the science is. And so the good news is that New York City is thinking about these issues, and they're hard issues. Even there's a 12-member task force, there are 4 techies on it, some lawyers, policymakers, city agency people, and some techies like myself. And even defining what an accountable decision system is has caused a lot of, raised a lot of issues just within the task force, let alone how is a city agency supposed to operationalize this. So the Columbia University works very, very closely with the New York City government, partly because the Data Science Institute was first created out of the Economic Development Council that New York City had under Mayor Bloomberg's watch. So we have a very good relationship with city agencies and the city in general. And they do look to us for conversations, for leadership, for thought leadership, and so on. On campus itself, we have a lot of people interested in different aspects of the community that you mentioned. We have really strong interest from the School of Social Work, from the School of Public Health, and other parts of campus. And those people are working directly with community organizations, also working with the underserved youth in the city, all sorts of activities going on. With respect to your second question about every one of us getting different pieces of information, this has just been exacerbated by the ease of the digitization of information, the ease of disseminating, and now the ease of changing, altering content. We've been working at Columbia with the School of Journalism in general about things like fake news and how to combat that. It's, as you know, it's not there's no easy answer to this. And it's, just deciding when a piece of information is authentic or not is not an easy answer, question to answer. The Data Science Institute is sponsoring a couple of seed grants that are looking at these kinds of, what kind of technology can we bring to the table to do things like veracity checking and so on. But these are, really research ideas. So that's what I can offer in terms of what we're doing.
Thank you.
And this is the last question.
Eric Lindahl, Stockholm University. Great talk, Jeannette. I very much agree with you with the importance of keeping the data open and sharing, not necessarily, well, it's good in the sense that we all develop faster this way, right? And I think computer science as a field has benefited tremendously over the last few decades by being very light on patents, or at least we don't use patents. But I can also see, as we're starting to commercialize this, which will surely happen the next few years, and we get the medical industry and everything involved, there is likely going to be a greater and greater demand for also monetizing this. And then I bet we're going to see more and more patents. And there I start to get a bit worried, because on the one hand, I like commercialization, and I like my healthcare to be better, but patents are suddenly going to start offsetting things that I can't compete with you for 20 years or something. So do you handle this in your position leading a data center? And do you have any policies about this? Do you want to, not just the data to be free, but also the way, what we do with the data?
Yeah, this is another one of those questions that there are multiple sides to. I'm a great believer in open science and being transparent and the conduct of science as we know it today, which is being open, sharing results, sharing data, sharing algorithms, sharing. But there is what you're saying. Now, the implications that you're talking about are more about the commercialization, and then we're talking about the IP and patents and so on that go with that. I haven't really thought about commercialization so much in terms of the great work that we're producing. I've seen more, what concerns me more right now is that a lot of the advances in computing, especially in AI, deep learning, machine learning, and so on, are happening in industry, not in academia. And I think this is concerning for a couple reasons. One is industry has a different mission from academia. It is about bottom line. It's not about advancing science. It's not about discovering new knowledge. And right now, industry has the data, and they have the compute. The data academics will never get their hands on. That is an asset to a company. Compute, yeah, well, maybe the commercial cloud providers will provide some free cycles for some amount of time, some amount of free storage for some amount of time, but that's not how science works. So I'm concerned about that. And there are different ways in which we can think of perhaps about industry and academia working together. I think we need to have a conversation about that. The other reason I'm concerned is that maybe, and I know you heard Jeff Hinton and Jan LeCun talk about deep learning earlier this week, and I just want to say that Jeff Hinton and I were colleagues at Carnegie Mellon together in the mid-'80s, and it was just, you know, just what he probably said. In the mid-'80s, no one believed me. Well, in the mid-'80s, we were all humoring Jeff, and now look at what happened. I want to say that maybe, and I don't know, I'd say maybe eventually deep learning will hit a wall. And then what? Is that not the role of academia, to know what that next thing is? We should be, we probably are already, we should be thinking about what after, what comes after. So it's one of the, it's about, this is the, you know, the NSFer and me talking, it is about supporting, and Microsoft Research, it is about supporting basic long-term research. And that is the role of academia for science.
Thank you so much.